So this workshop is going to be on RAG applications and how do you build applications around LLMs and basically extend the knowledge capabilities of an LLM. And the main focus here would be to take it from a development environment all the way to production, all the design decisions included in that, and the tech stack that comes with it. So a little about me. I'm Leoshish. You can just call me Dave. I'm a technical coordinator here at ACM and a master's student. Also, I work as a computer vision and graphics research assistant at ICT. I have some open source contributions with NLTK, semantic kernel as such. I have my own YouTube channel where I post educational content, and basically I'm working on a Minecraft clone for like 4 years now, and I just upload progress videos and some demos about that. And I've been working as a full stack engineer for Dell Technologies for almost 3 years prior to coming to USC. So all my social links are up there. If you want to connect with me, feel free to do that. I'll have that links at the end of the presentation also. So let's get on RAG. So what RAG basically means is retrieval augmented generation. So you take an LLM and you essentially connect it with your own data source. No, that dial. And so you can just continue over there then. So you take an LLM and you connect it with your own data source. It can be a vector database or any of it. And depending upon what the user asks, you search for relevant knowledge and pass that and the user prompt to the LLM to give a better answer that than an LLM would do on its own, right? So basically, like I'm sure all of you have worked with ChatGPT before, and usually the way you interact with that is you just do basic prompting. You try to manipulate into thinking ChatGPT of a particular way so that it can give you an output. Like a prompting would include you say tell ChatGPT to think of it as a lawyer and tell it to explain to you about some legal procedures or some legal advices. But that doesn't actually extend the LLM's knowledge. It's just faking it to be someone. It doesn't know what exists outside of the data it was trained on. So by connecting it to a vector database, you can provide it more information as required, depending upon what user is asking. So you are essentially extending its knowledge base in a sense. So this also gets around the limitations where LLMs are usually trained on a particular data set and they are frozen to that. They can't do anything that's outside their capabilities. Like ChatGPT, I guess, was trained till a corpus of 2021. So if you have a new technology whose documentation came out after that and you want to ask questions about that, you can have it be integrated with a vector embedding database. And now to create a complete, let's say a RAG application from the start, there will be like a lot of moving components involved here. And it might get a bit overwhelming as I'll try to introduce you to all the components there are, but think of it as only using what you require. So treat of this as like an introduction to all the different components that are involved, because at the end, the demo I'm going to show you is a fully working production app that's deployed. So I want to take you through it and help you get understood with like what are all the components and how I try to bring down the costs of deploying the RAG application. So to start with here, how many have you have worked with Docker? Like just a show of hands. Yeah. And among the rest of people, how many of you feel like that you should learn Docker or you want to try doing something with Docker? Sure. So like one of the key takeaways I hope you have from this presentation is like you understand the usefulness of Docker and how it can help you in any of your daily workloads, whether you're just using whether you're working as a data scientist, a machine learning engineer, or a complete suite. And Docker, like I won't dive deep into how that Docker actually works, but just like on an overview, Docker is used to containerize your applications, and the way it does it is using a Docker file. And you should consider Docker file to be and analogous to a shell script, you basically define commands on how to package your application. It could be like copying files over, setting up some environment variables, or exposing some ports. And finally, what you end up with is a runnable container that you can ship around to cloud platforms on or your local devices. And as long as you have a Docker engine installed on the device, it will be able to run that application. So it eases the deployment. And one of the biggest issues you face is like something may work on your machine, but it doesn't work anywhere else. And that is exactly what Docker tries to fix. Other than that, it helps you with rapid deployment and fast setting up of development environments, right? You don't have to install a lot of dependencies if you have a container already there. And the main goal of what Docker does in the demo that I'll show you is the orchestration, because there are at least 5, 6 microservices and they need to be started up in a particular order. And they need to be served as one single unit to the user. So Docker with Docker Compose helps me orchestrate all that and helps me create the cluster in a very predictable environment every time. Next is a language model. A RAG app is nothing without the actual language model, and there are multiple options for your language models. Like there are hosted cloud options. You can connect to ChatGPT with their APIs. Gemini, Azure also offers its own open AI offerings. I think AWS also has an AI offering. Or you can host the models on your own using Olama, with which you can download Llama 2, Mistral, and Orca models. And when you're working with these language models in a RAG app, you don't need to know at all how they're working under the hood. Just think of it as any other API. You just call these functions with the provided parameters. It's basically a normal system function call for you. Now, on top of these LLMs, there are some orchestration frameworks that provide you more APIs to help interact with LLMs in a much more structured manner, like LangChain, Llama Index, and Semantic Kernel. I think there are more coming out now. But the main goal of these LLM frameworks is to provide you capabilities to either chain multiple prompts one after the other, or they'll have some templating engines built in that can transform your input into a proper markdown format, or it can add instructions so that the LLM gives you a JSON output. And usually these transformations are very well tested out there. If you try to do them on your own, you'll have to basically prompt engineer them, and it might work, it might not work. But the transformations provided by these frameworks are usually tested in a lot of cases, and I won't say they are guaranteed to work. Nothing is guaranteed to work with LLMs, but there's a high chance they will work in most cases. Now, now we have our LLM and we are able to run it, but the main part of RAG is to able to extend the knowledge. And to do that, we need to provide LLMs with the knowledge. Now, LLMs don't understand text or the text we humans understand at all. So we need to transform the knowledge, the text, into something LLMs could understand. And that is basically just numbers. And we call that embedding. So basically, if you have a passage of text, you convert it into a big vector. The dimension of this vector depends on the embedding model you are using. And once you have these vectors are stored in some kind of a vector database. Now, as a new user does a query, you take that query and also create an embedding vector for it. And then you find the similar vectors. It's like a normal distance search or a cosine similarity search, what it's technically called, with the vector database. And you'll essentially get text or content that is similar to what user is asking for. And that as a whole package is passed over to the LLM. And all of these LLMs actually have their own embedding generation models, and you could use them, or the one I prefer is the All Mini LM6. This comes from Sentence Transformer. It is not that high quality of a embedding transformer, but it's pretty fast compared to if you use the Llama 2's embedding model. It will be a bit slower to compute it. And the vector store is also important. This is where the actual embeddings are stored. And the vector store would also provide you functionality to do similarity searches. Most of the existing databases now are coming up with vector plugins, like MongoDB has a vector plugin. Neo4j, and even SQLite has vector plugins. And there are dedicated vector databases also like Quadrant or Pinecone. Uh, I personally haven't used dedicated vector databases because I find using databases which provide other capabilities along with vector search give you more control over the vector retrieval query. So this again something I'll showcase in the sample on how it makes it more powerful. But the main job of a vector store is to provide similarity search. And finally, you have all this APIs or all these LLMs ready. You need to serve it to the users. So you need some kind of backend API or an HTTP server so that at the end, you want the user to interact with these systems. And for that, you need to provide them a good user experience. And that user experience usually talks to some backend API. And there are countless options. You have like simple options like Fast API for Python or Express, or you can go to the most complex of options out there for enterprise grade, like Spring, ASP.NET or something. But this is something I'll totally leave up to you. So you should try to use whatever you're most comfortable with. But if you want some good starting options, I would recommend Fast API for Python, Express for JavaScript, and ASP.NET. Like the modern .NET is also pretty good. It is something I feel most people don't have the correct perception about, but if you have some time, you could try it over. I would recommend it over Spring and Java. And finally, the front end, again, it's totally up to you if you want to provide a web experience or a mobile experience. But one thing I would mention here is Streamlit. Streamlit is like a Python framework which you can use to convert basically your Python notebooks into a full stack application. It does all the networking and the routing for you. It has built-in UI components and a theming library. So creating a full stack runnable, interactable user application could take just like about 20 lines of Python. The only downside is that it is a very resource hungry. It is a bit like it takes a lot of resources to run because it's trying to do everything in a dynamic way. And if you don't want to go a Streamlit way and want to develop a proper full stack or a proper front end application, again, good options to start with would be SvelteKit for web and Flutter for your cross platform needs. Now, the secret sauce for my demo that makes it low cost is a VPN. So if you try to run a LLM and a vector store and you want to host it on a cloud platform, it's going to cost you a lot because LLM need GPU compute capabilities and these capabilities come at a cost. So what I thought of was like, I have old gaming laptops there in my room. So I just installed Ubuntu servers on them. And using a VPN, I was able to connect those systems to the Azure cloud systems. So I could have my front end application running in the Azure cloud, and all of my compute intensive resources were running right in my room on my old gaming laptop systems. So that way I could serve a RAG application to everyone out there in the free tier of Azure. So you save up a lot on your GPU compute costs, on your database storage costs. And as USC students, we all have access to Tailscale, which is a VPN. You just need to log in with your USC account. There is a performance impact of it that comes due to the latency, but if you're just making a demo application or a project that you want to showcase, I think this is a perfect way to go about it. Otherwise, it's going to cost you a lot. And as far as the Tailscale VPN is concerned, I've used it a lot to host Minecraft servers and other game servers for my friends around USC. So it has very nice integration with Docker already provided, so you don't need to set up any of your networking stuff. So now that I've covered all the major components that go into building the demo application, let's go over the actual application. So it's called Corgi AI, which was short for Community Retrieval Augmented Generation AI, but the community part was never implemented as I was short on time. But I'll just show you the application. So as you can see, I'm going to a particular IP address, and this is because this app is still hosted on my server back in my room. So my laptop here is connected to that server using the Tailscale VPN. And if any of you log in, like set up Tailscale VPN on your system, you can also go to this particular address and interact with this application if you want. So what this app basically does is, right, it goes over multiple Stack Exchange websites like math.stack exchange, physics.stack exchange, and I have scraped a lot of questions. So these are the tags and the amount of questions for each tag that are currently present in my database. And the only limitation for scraping was like after a while, Stack Overflow bans your IP unless you're a registered third-party developer with them. So you can't like run it all overnight and have everything scraped. For this demo, I had questions on Docker, thermodynamics, and quadratics. These are the primary three tags I scraped, but most questions have multiple tags, so I got other stuff with it also. And you can currently chat with it, and it will give you answers by considering the already asked questions on Stack Overflow and provide you a better answer. And it also has quiz generation capabilities where it will take those question answers and generate quizzes for you. The last part, the knowledge graph part, is something I really wanted to develop, and I'll talk about how you can go beyond drag applications later in the presentation. So let's just say chat. If I just ask it, how do I integrate e to the power x? Now, it is not at all guaranteed that it will ever return a correct answer. It might sometimes return wrong answers for like simple questions also. And this does take about, I think, 23 to 30 seconds. Or sometimes my systems back in the room crashes also. But the quality of answers this depends on the amount of vector data you have. So like asking this kind of question, a similar question might not exist in my database, but if I ask something very similar to what has already been asked on the Stack Overflow forums, you can expect a nice answer. Okay, so it did come up with some kind of answer, and clearly it is wrong. And but the good thing is it will also provide you the sources of like what all answers is considered to solve this question. And you can go to these links and this will be like actual Stack Overflow posts. So one of the questions that I know has a very similar answer, or a question like a question exists in my database, is basically, why does the shower curtain stick to me in a hot shower, right? So I just changed the topic to physics and I asked this question, and this is something it will give a close enough answer using the thermodynamics principles, hopefully. But again, you can see this is taking around, so the last answer took 40 seconds. And it is a bit hard to read what is the actual model it's using, but it's the Llama 2 7 billion model. You could go to a 13 billion model, and this number of parameters just dictates the capability of that model. The reason I'm sticking with the 7 billion is the system I have is just has 8 GB of VRAM. Other models just run out of memory if I try the 13 billion model. And usually 7 billion with some quantization gives you a fast enough result. Okay, so for the second question, the answer is already here. And as I said, there is already existing a Stack Overflow question, which is very close to it. So it just summarizes that question and answers this one. As far as the quiz generation is concerned, it's a bit complex because like normal question answering, there is no prompt chaining involved. You just take the vector and you just use one prompt and it will answer you that question. But in a quiz generation thing, so let's say I select thermodynamics and quadratics, and I'll tell it to generate 5 questions for me. Again, these questions do take a time because for each question, there has to be at least, I think, 4 LLM invocations. And the way it does is it will take a Stack Overflow question randomly from that topic. It will summarize the actual question, then it will summarize the answer. So that are 2 LLM invocations. Then it will take those 2 summaries and generate 3 wrong answers for me. that is another LLM invocation. So with these three LLM invocations chained after one another, and chaining them is very easy. You just call the same function and again, and the actual prompting is just a simple text file. So there isn't much to do that. But again, the quality of answers won't be that good. And I know in my this quiz, like the question generation scenario, any answer that looks too different from the other three answers is usually the correct answer. So since this answer has two lines, I'll just go with this. And okay, this, and that's not always the case, but here you can see like sometimes it will just say, here is the answer statement, and you could be confident. Now, these quirks can be worked around by using a much higher parameter model. Like you can use just ChatGPT directly and it will give you 175 billion parameters. And sometimes if the question is small enough, it does generate you good options. But again, just go with the most different option and it will generally be correct. Is okay, clearly the first question I messed up, but yeah, you do get a proper report and you can also go and see on the source from where this question was generated. So these were the two capabilities I built for this application. And this application was submitted to HackSC last semester, where it won the best use of AI. I also submitted it to multiple other hackathons. One of them is not listed here, which was the Microsoft Semantic Kernel Hackathon. That also this one won. So, and I'll share all these links at the end also in the PPT. It has a much more deep dive of how like we went about the ideation process of making this product. So this is more about that. But this presentation, I want to focus on the technical aspects of achieving this product. So the let's see the source code for this project is open source and it's available on GitHub. So you can just go to my GitHub profile and go look at it. And I'll just be going through this source code and explaining it in a more detailed way of what's actually happening. I hope you are able to see the screen. I'll just zoom it a bit. Now, how to zoom in this thing? Pump up the font size. Yeah. So So the overall structure of this application, you can see on the left side, I have the apps folder, and there are about, it says 6 applications there, and each of that operates as a separate like microservice or a container. And all of them like talk to each other to actually give you the final results. And each of those folder is gonna have a Docker file that defines how to build this particular application. And at the end, it's all connected by this final Docker compose file, which which dictates how do I take all the 6 of these applications, put them together, and serve them in an order that makes sense. Now, Docker and Docker Compose are two different things. Docker is limited to building just one container, and Docker Compose is a separate tool which helps you run multiple containers at once. So it's more of an orchestration thing. And a Docker Compose file is just a YAML file. It just contains some configuration, some key and values, which you can easily go over the documentation to understand. But the key thing here is the services. So each of these services is like one different application. So we'll just go over them one by one. And the last part you see the networks part, that is it's just done for like security purposes. In Docker Compose, you can define your own network. So I just said this network is called CorgiNet, and I've assigned all these applications to CorgiNet. So anything outside these networks won't be able to talk with these applications. It's just a security consideration. It's not at all required. So let's go look at the first, how the LLM is run. And in Docker, you share stuff by creating images, and these images are hosted on Docker Hub. It is like a centralized repository. There can be other repositories also. So the LLM uses the Olama image. I haven't created this image at all. It comes from the Olama developers. So I take that image, I mount a volume. That's line 8. Now, mounting volumes is a way to add persistent storages to your container. Usually your containers run in isolation and in a sandbox environment, so they are more secure also. But these volumes help you to persist some data between multiple runs. Your container may crash and you don't want to lose some data. So generally, volumes would be used for anything, anytime you have caches, anytime you want to share some data between containers using the file system, or if you're running a database in a container and you want to persist the actual data of the database. So wherever that database stores this data on the file system, you mount a volume there. So that's what the volume tag is. The profiles tag, this is something very specific to the LLM. You won't see it anywhere else. I just looked at the documentation why this needs to be added, but the Olama image can only run on a Linux environment, so you have to add this. The ports tag is also very important. This is how you expose the ports that you are allowed to connect to. So like by default, Olama exposes this port, and that colon syntax matters a lot. So on the left side, you have the port inside the container, and on the right side, you have the port outside that is exposed. Usually you'll find both of them to be same, so that way it makes it easier to just do the request to that port. But you can change that if you want to export your application on some different port through Docker. And finally, this deploy part, this is all done to provide this container GPU capabilities. That's it. Uh, Personally, I don't have any idea how the NVIDIA GPU capabilities work in containers. I just copied over this deployment part. And with that, your LLMs will use the GPU to do the computation. Next is the Neo4j container. So as I mentioned, we need a vector store for our embeddings, right? And the one I'm using is Neo4j, which is a graph database. I'll go in much more detail about why Neo4j and what are the benefits of Neo4j at the end of the presentation, as it will help you in the vertical if you're making an app for the connection vertical. Also, Neo4j could help very well there. But essentially, Neo4j exposes two ports. One of the port is for your applications to connect, and the other port is for like a Neo4j graphical terminal to connect. So you can actually look at the data, which so you shown, and you have your volume mounted. That's where the Neo4j stores its actual data. So you want to persist it. The environments key allows you to set up some environment variables. So I just provide the default password and user account I need to connect with. And the plugins, we need the Epoch plugin here. Again, this plugin enables the vector search capabilities in Neo4j. So by default, this would be disabled. So just copy paste this one line. Health check is something that is totally optional, but it's a good practice in the industry that we usually use on our production servers. So back when I used to work for Dell, all of our applications used to have a health check URL, and we'll have like a centralized dashboard that would ping all those applications in a particular interval. And that way we'll basically get to know whether something is working, something has crashed or not. So your database can have that health check, but I don't use it at all. I just copy pasted it long ago and remove it probably. And so that would be covering the LLM and the Neo4j. So these two are the two services that I didn't create at all. I use existing images and I just configured them to run inside my cluster. But the next all services, this is what we have created. This is where our business logic lies. So first of all is the PyLoader. It just stands for the Python loader. And this is like a internal, you could say an admin dashboard, which you can go and this will help you actually load the data into your vector database. So if you look at the file loader Python file, so again, this is a Streamlit application, so I don't need to create any UI for it. So I'll just go over the basics of what this application does. So all it does is, right, it will have like a Stack Exchange API URL, right? And these URLs all come from the Exchange documentation. They have a nice API documentation. You can just go there, try out dummy requests and figure out what parameters and what query parameters I do need to pass. So I have that URL here, and the .env file, which I should note is here. Like at the top level, I have a config folder which has a file which contains all the environment variables that are used by all of the 6 applications. It's like a centralized configuration for my application. So I load this, that way I'll get access to all these environment variables. So I need my Neo4j connection parameters. I need parameters to my embedding model also, since I'll basically take the data from whatever the Stack API returns. I generate an embedding out of that and put it into Neo4j. So that's what's happening here. And then once I got all my configuration ready, I set up my Neo4j connector. So I just connected to these methods come from the Neo4j driver for Python. You just connect to the graph. You provided the URL, username, and the database name. Similarly, the load embedding methods, it's a custom method I have, but it's built on top of the LangChain embeddings. So depending upon the configuration, I could either use the Llama 2 embeddings or the all mini LM embeddings. And I generally prefer the second one. As you can see, the dimensions is much less than the Llama 2 embeddings. So the quality will be reduced, but it's much faster to compute and to perform the vector similarity operations. So once these are uh, loaded, I create some constraints and vector indexes. Constraints because I don't want there to be multiple vector embeddings for the same thing. There should only be one instance of that. So I just create a constraint. I'm hoping you're a little bit familiar with SQL and how databases generally work. And a vector index is the actual underlying data structure that Neo4j will create to perform fast similarity searches. So we just initialize all that. And then this is the complete importing method on it just starts from here, right? So since it's a Streamlit application, I only need to define my render page function. So I give it a header, a subheader, a caption, and it will all lay it out nice in the UI. You can actually go visit this application also. I remember the port number. Yeah, it's 8100, right? Now, usually this Streamlit dashboard is supposed to be an admin only thing. It won't be exposed to the users, but you can kind of map it out of how that is it. So that render page, you see, right, I'm setting headers and all, and how it actually looks in the Streamlit application. So it's a very nice way to create your user interfaces fast, and it will do all the underlying networking requests for you. So you don't need to do any HTTP requests or anything. So it makes it a good candidate for creating your user experiences fast for a hackathon. So I just have a target button, and whenever this button is clicked, this function is called in the backend for me, which will just go over in a for loop. It will, whatever pages I specify, if I tell like I want to load 10 pages of questions, it will go over that for loop. It will create a query string. These parameters I get from the Stack Exchange API documentation. And once my query is created, you do HTTP request. Once you get the response is then inserted into the Neo4j database. Now, this insert data function is something we can look into. So what insert data will do, right? Okay, actually, before this, the embedding generation also happens. Yeah. Okay. So this embeddings here is the actual, you could say it's like a closure here, but this embeddings objects provides the capabilities to generate the embedding. So we just pass it into that function, and that's where it's actually used to generate the embeddings. So when the insert data happens, I get the total number of items I'm going to be inserting. There is some text pre-processing that happens. Again, these keys of whether it's title or body all come from the Stack Overflow documentation. So I concatenate the title and the body into one text. The answers are also all concatenated. And I don't take all the answers, it's just the accepted and the two most popular answers. So these things are concatenated into single text or the string objects, and that's where the embedding is generated. So I have a question embedding and I have answer embeddings also because I want to be able to filter on them differently. This for loop is a bit, I would say, resource intensive. If I try to load more data now, it would take like 10 minutes to actually go over Stack Overflow, generate these embeddings, and essentially insert the data into the Neo4j database. Now, this is the actual import query. It's a very scary query right now. So I would not go over it right now. Once I give you a bit of the overview of how Neo4j works, this query won't look that scary. But essentially, it creates multiple objects inside the Neo4j database. Your question is a separate object, your answers are a separate object, and they need to be connected to your correct filters. Like each question belongs to a particular site, whether it's from math or physics, and each question has some tags. So since it's a graph database, those edges between these objects need to be created. And that is all is defined in this query, like how do I connect up all this data? And the metadata of those objects, if it's an answer object, whether was that answer accepted, what was the score of that answer, the creation date. It's all transformed into a Neo4j representation, and that is what the driver executes. And that's how you get your vector database up and running. And you now have the capabilities to do the vector similarity searches. So if you go back to the compose file, that is all the PyLoader is doing. It's an admin only application, and it is responsible for importing data into your vector store. Next, we have PyChat. Now, this is a LangChain implementation of the chatting capabilities. It's no longer used in the application, but I still have it because the one I use it is the quiz API. That's where the semantic kernel implementation exists. But you can use this example to see both how LangChain works and semantic kernel. The only difference is the PyChat is written in Python and semantic kernel is written in C#. It is the semantic kernel is much more performant, but PyChat might be much more easier to understand. The application is a bit simpler to understand. So again, you set up a network, you expose some ports, the volumes are mounted here because the embedding model generates a lot of cache, and if we don't cache it every time you do embeddings, remember the chatting also is doing embeddings. That's depending upon the user query. So we want to cache that. And another thing you'll notice is I have a depends on tag, and these depends on are basically other services. So what Docker Compose will do is it will only start the service when these other conditions are satisfied. That means my pull model has started successfully and my Neo4j is healthy. So this way I can guarantee my cluster always starts in a deterministic manner. If I have some initialization code that is like connecting to those databases, it only happens after my database is actually up and running. So you can use this depends on tag to control the initialization of the Docker cluster. And that reminds me, like this pull model is something we haven't gone over. So let's just look at this also. To pull the Job of pull model, again, this is something that I didn't create. I copy pasted it from somewhere. But when you run the Olama instance, by default, it doesn't download any model for you. So you actually need to tell it which LLM model you want to use, right? And so the job of this second container is call the Olame API, tell it to download whatever model I have specified in my configuration, and then just exit. Because the downloading part, depending upon the model, can take 3 minutes or 20 minutes also. If it's a 70 billion model, these are like huge 43 gigabyte files. So this pull model is very essential to the startup of my cluster. There is a very particular order because the LLM is the first thing I need to be alive before I can have any other thing started. So all of the services will depend on whether the pull model service has completed successfully. So that way, I'll never have initialization errors. And if we look at the pull model code, it is actually just one Docker file because the actual code is just a script. And here they are doing script in Clojure, but you could have it done in like a JavaScript, a shell script, a Python script. All it does is does a HTTP request to the Olama container. It tells it to download the model you want. The reason it's done in Clojure is I have no idea. Like from where I got it, it was like this. So there's no need to reinvent stuff that you don't need, right? Right. And the final two are the most fun parts of how this service works. Uh, One of them is the quiz API. So the name is a bit misleading. Right now, the quiz API does all the backend functionality. It's like a big monolith, except the embedding generation part. The reason is because the quiz API is something I started later on. It's after the hack SC happened, and I wanted to rewrite the complete application in C Sharp. One of the main issues with using Python containers is, right, your containers will usually be around 8 to 6 gigabytes in size, even if they don't have anything else. Like if you look at the PyLoader, which I showed you, that's a 8 gigabyte container, and it is just a 100-line Python file, which is pretty surprising, right? The biggest issue is when you install Python dependencies, there are a lot of, it installs a lot of things, it compiles a lot of things from C, and that generates a lot of binary objects, which take up a lot of space. But my quiz API that's done in C Sharp, it has all the semantic capabilities. It has a LLM orchestration framework in it. But this container is about 150, 140 megabytes. That's it. So, I mean, there are other optimizations also from a Docker point of view that I do, which if there might be time, I would go over them. But the main reason you want to get your container sizes down, it impacts your startup time, first of all. And if you want to deploy these containers on a cloud provider like Azure or Google, you have to upload these containers there. And that, like if it's an 8 gigabyte container, that will also cost you some storage, whatever the storage cost is. So you essentially you need to get them as down as possible. So the Quiz API is a complete .NET application. I won't go over the internals of it because it's a bit bigger application, but I will show you the prompt chaining and how that happens because that is done in text files only. But you always have the source code, and if time permits, we could discuss this further. And finally, the actual app. This is nothing but a front-end SvelteKit application. This also you'll see depends on whether all the Neo4j and the pull model is healthy, and it just serves a static website. But to be honest, out of all the things that took development time, the front end took the most time to develop with, but that's just how front end development goes. Looking at making it look good, making sure all your interactions and your form handling is done correctly. And it is the most boring part also. And I think that is the reason I gave up developing this application further because I could get new functionality done up in the backend very fast, but front end development is slow. So that's why I would recommend go with Streamlit or something so you can get to your features and your product to users as fast as possible, get the feedback, and only then when you are sort of finalized what you want to do with your front end, make a dedicated one because that is where you will consume most of your time in. So But I think the main key takeaway that you get here is how Docker and Docker Compose is helping me to orchestrate this complex application with so many moving components. I just need to run this one make command anytime my app crashes. I just run this make run d command, and it will have my complete cluster up and running in about 60, 70 seconds. And I'll show you the VPN part also, how this cluster is able to connect to the Azure services. So the actual app is the only thing that runs in Azure. Rest everything is running on my server in my room. So if you look at the Docker file for the app, mm, so it actually has two Docker files, the local Docker file and the main Docker file. The local one is one I used for my local development if I'm running the app also in my local server. But if I'm running it in the cloud, the main part here is this. So you copy stuff from the tailscale image also. So you essentially get the tailscale binary in your container, and you can use the tailscale CLI to just log in into tailscale. Uh, when you log in into your tailscale account as a USC student, in the dashboard, there will be a way to generate an API key so that way you can log into tailscale. Like your Azure containers can log into that. And as an example, if I see my devices, you'll see there are a lot of Azure containers listed here. And some of them are pretty much dead. I don't think which one is actually working right now, but this is how my containers in Azure are able to talk to my server here. And if you do log into Tailscale with your USC IDs, your name will also be listed here, and we can actually access each other's machines. So be careful with what ports you are exposing with it. Right. So I'll just give you a rundown of what the Docker file also looks like. As I said, consider it to be analogous to a shell file. You have like commands like copy, run, expose directory, creating working directories. It's very similar to a shell file. But the key things here is like this from command. So the from command tells which is the base image you want to start with. You don't want to start with scratch always, right? So if I tell it to start with from node, I already have node installed. Some of my other dependencies required for node installed, right? Then I set a working directory and I copy over my package JSON and the yarn file. These are just, if you haven't worked with Node, these files just define what dependencies I need to install. Then I run a yarn. So the run command just runs a bash command. So I just install the dependencies. After the dependencies are installed, I copy over everything else. This will bring in my actual source code. And if I have some assets, images and other stuff, I do a production build. So another key thing to remember is your build needs to happen in Docker. If you do a build on your system and move your deployed files into Docker, it might work. I think for Node, it would work, but usually builds are system dependent. And your system could be a MacBook, but your Docker container is running a Linux system. So your build needs to be for that Linux system, right? So that's why it's a good practice to have your build command as part of your Docker file. So once we do the build, right, I put another from command here. Now, this is something you won't find in most Docker files. Most Docker files will only have one from command, and that's at the top. The reason I do here this is something called as multi-stage building, and that is only done for the purpose of optimizing size. This is completely optional. You don't need to do it. But essentially what happens here is I create another fresh node container and I copy over only the stuff I require to that container. Because the issue is when you do yarn install, the way Node works is it will first download the dependencies into a temp folder and then copy it over to your project folder. So you essentially have two instances. So that is doubles the size. The same happens with pip, the same happens with your Java and Gradle, and the same happens with your .NET. All of these package management systems usually download stuff to a temp folder and then copy it over to your project folders. It is an optimization for them because if you want to reinstall that thing again, you don't need to do a network request, but it does use a disk on your side, right? So we don't want that thing to be in our new container because we have to pay for it at the end. So by creating a fresh container and just copying over the stuff we require, we don't get that temp folder again. So you can reduce, I have seen, especially in Python container size reductions of 3-4 GB using these multi-stage builds. So, and you can name these builds. So this one, like I call it runtime because this is the actual final build that I'll be doing. So again, I copy over stuff and I do another multi-stage for bringing over the Tailscale stuff also, right? Because when you install Tailscale, it will install some dependencies or some private files. So you copy all that over. And finally, in your Docker file, you'll expose the ports that you want your container to expose, and you just define an entry point. Now, this entry point is what your Docker container will run when it actually starts. This could be npm start Python 3 and your Python file. I start my container using a shell script. And that shell script, all it does is, I can find it. Yeah, the start sh. So it just does a Tailscale login and it starts my node application and passes some environment variables. So this is how I'm able to connect my clusters running in Azure to my local servers. So all this technical side aside, now let's look at the actual prompting and how that is done. So I'll just go over the PyChat, which is like the older implementation. So PyChat is just a fast API application. The main Python file just has some HTTP routes defined, and they all will at the end call this chains.py file. This is where you have all your chains configured. So this is like a question answer chain configuration, and you can see the prompt here, how you design your prompts. You basically you try to tell the LLM what it needs to behave like. If you want it to behave like a teacher, you want it to behave like a doctor. You also give it some more instructions what to do and what not to do. Nothing is guaranteed. It will try its best to do all the stuff that you're trying to tell it, but there are limitations with context windows. Like every LLM will have a context window for like, I think for Llama 2, it's like 4096 or something. And that context windows just tell how many previous words it will look at to get the next word. And if your actual prompt is too big and your instructions are at the beginning of the prompt, as your LLM is generating text and while it reaches the later stages of your answers, it might not look at your instructions. So you could get bad results. And one way to fix this is to break your prompts into multiple invocations. So you do smaller steps and you pass the results of the smaller steps into one after the other. That's why summarization prompts are very helpful in this thing because they can reduce the text size. And any other things or techniques, these all depend upon your domain specific and the business specific logic. If you can bring down the text size, try to get it as small as possible. It directly impacts your inference time and the quality of your inferences. So in this chain, you can see like you have like a system template. This is what we provided, and that summaries part. This is where the whatever you get from the embeddings is injected in here, right? And then there is the user template. This is generated from whatever the user is asking. And all of this is in a kind of a markdown format. LLMs understand markdown format, so you can use that to put emphasis on something or not. And that's like a smart way to put importance on stuff. And markdown, usually markdown formatting doesn't take up much characters also. So that's helpful. But there are other templating engines also that you can add. This is again provided from these LLM orchestration frameworks. If you want output in a JSON file, you can do it, but always validate that JSON file afterwards, whether it's a valid JSON or not. So once you have the system template, and the human template, we combine that into a set of messages, and these messages are then passed over to the LLM. And this here is the actual vector retrieval query. This is where the similarity search also happens. Again, once I go over Neo4j, this will become a bit more clear, but all you need to remember here is like, this is the retrieval query. I'm retrieving the question links here. I'm also passing in the site here. I'm doing string interpolation here, which is not at all safe. Don't do it. But there was a limitation here and I had to do it. And I, and it is one of the reasons why I moved to a C# API, which I'll show how I fix these limitations there. So once you have this, you can just configure your chain. So now this from Neo4j from existing index, this function comes from LangChain. So you just need to provide it a lot of configurations, like what is your, so that embeddings object is basically an object of how you can access the embeddings, the graph URL, your Neo4j username, password, database, the actual index name. This index name is something that is generated by Neo4j for you. So you run it once, you find the name, and then you hard code it here. And what is the index property that you're embedding? And I'm just embedding the body properties of all the questions and answers, right? And at the end, you give it the retrieval query. This is the query it will use to find the similarity searches. So once this QA chain is built up, again, there are some other parameters like you can set a temperature, you can set um, like the K values. These are all LLM specific parameters. I frankly don't know what most of them do. You can go read up on their documentations, but a temperature, like some of these parameters control the creativity of LLM, like whether it will try to be more creative and give you out of the box answers, or it will try to be more restrictive and give you answers very specific to the topic. So once this chain is configured, this chain is exposed to the actual HTTP APIs, and they just pass in a string, get an answer, pass in a string, get an answer. And that process happens continuously whenever the chatting with the LLMs is happening. You also have the quiz LLM chain here. This was my early implementation to try to get quiz generation working from LangChain. I don't think this was completed, so I'm not sure if whether it will even work, but right now this function is not called at all because, as I said, like for normal question and answer, we are just doing a single prompt execution. But for your quiz generation, there will be multiple prompts. And that is something I can show you in the .NET API. So, so here is my .NET API. If you do sometimes decide to actually look over the code, so I'll just tell you where the prompts exist. You just go into the quiz API and inside the kernels, you'll have your chat kernel and the quiz kernel. And inside your quiz kernel, the skills folder is all your prompts. And these prompts are just text files, right? And these text files are loaded by semantic kernel. So it is a way to externalize it. So you don't need to hard code this in code. So it's a bit easier to work with. So, and you would see these prompts are much simpler also because for some reason, semantic kernel was giving much better outputs with simpler prompts, which is kind of true also. You don't need to over-engineer your prompts. And there are other prompting strategies also, one of which I very like is example strategy. So sometimes what you want to do is like requires a lot of instructions to describe the whole process. So instead of putting in a big prompt using descriptions, what you can do is you can just give the prompt like 5 examples. If this is the input, this is the output, this is the input, this is the output, and then the 6th thing would be your user input. So that way it can sort of figure out what you're trying to do and it can give you an answer. This is like one of the ways to compress large prompts. I'm sure you'll find others also online to compress large prompts. Always you can break up, like here I have broken up. So the way this works is the question prompt is executed. So it just says like given a problem statement, create a concise question statement. And I define some question creation rules. I think putting it in all caps puts more emphasis on it, but who knows how LLM works under the hood. So I just say don't waste word, be short, clear, concise. And this is something you'll just have to figure out with trial and error. And once you have the question statement, the prompt is for generating the answers. So this is executed after the question is executed, right? So I'm saying given a question and a long answer, generate a short answer statement. And finally, my uh, options prompt is executed, given a question and a correct answer, create wrong answer statements. This is the one I had to work a lot with because at the end, I wanted something that I could parse and create three strings, right? So at first I thought, okay, let's get a JSON output, but I wasn't guaranteed every time that the JSON I was getting is correct. But for some reason, this works. I just tell it to index it as ANS1 colon, ANS2 colon, and ANS3 colon. And every time the output I get, the answers begin with these tags, and I can then process that string based on these tags, divide it into a three-string array, and pass it back to my front end. But there are still times where this fails. So you need to have like redundant error controls or error handling in place. Otherwise, your UX will just break because it will otherwise be treated as some kind of internal server exception. So I think that covers the complete application. I'll just go over some resources that helped me build this application. The first one is GenAI Stack by Neo4j. It's not just Neo4j, it's like something Docker, Neo4j, Olama, like they came together and built this in collaboration. So whenever you install Docker, if you go to the tutorial section, GenAI is like one of the biggest things. They have it up there. And my application is pretty much similar to what they have built. They are also doing something with Stack Overflow. It's just I have extended it with question capabilities and accepting multiple Stack websites. They are just doing for one website and just the chat. And I think this has a much more deep dive into what's actually happening. And their code is also open source. So this is where I found the pull model Docker file also. You see like this one. This is where this is the file I copy pasted into my cluster also. Uh, this is where you'll find the original LangChain implementations also. So my implementations are very similar to these. So it's a good resource to get you started with. And let's just see. I guess I should have showed this diagram before. So this is like the overall architecture of my app on the moving components and how they are actually connecting together. So you can see you have the client, you have the front-end app, which exists in Azure, and you have your VPN, which connects to the cluster. Now, this particular architecture was done when I was submitting for the Microsoft Hackathon, and as a requirement, I had to use some of the Azure services. So I just moved my Neo4j data to their databases just to become eligible for the hackathon. But you can totally get rid of the rightmost Azure part. So this is how, but all these services, these are all hosted on my server. So this is like a bigger picture of that. Next, the kernel plugins. So if you do decide to use semantic kernel for like the C# implementation, by default, semantic kernel doesn't have Olama and Neo4j integrations available. I had developed them during the hackathon. They are available as open source libraries now. And the Olama connector is actually being contributed to the main Microsoft repository also. But I think it will take a month for me to finish up that work. But if you want to use it in the meantime for C#, again, this is available on my GitHub. These connectors are useful. And finally, the Tailscale documentation. So they have a very nice guide on how to integrate Tailscale with Docker to get your own resources up on cloud systems. And I mean, this technique you can use for anything at all. It just doesn't need to be limited for LLMs. Anytime you feel like your cloud costs are going up, and if you have hardware resources available, just connect them to the cloud and save up on money, right? So they have like a nice setup on how to connect it with Docker, Kubernetes, and it can go very advanced as you want. Right. I think that's it. Yeah, this summarizes all the technologies also used. Again, don't look at the Azure stuff. It no longer exists. But mm, but yeah, so like going beyond, right? RAG applications is something a lot of people are doing, and there is a limit to the quality of answers you can expect from a RAG application also. Like, but how do you make it be more accurate, more performant, and how do you make even like smaller models, maybe like the 3 billion model, to be able to give you correct answers? Because if in the near future you try to deploy LLM models on like mobile devices, you can't have like 40 gigabyte models running on them, right? So you want your small models to be as powerful and accurate as possible. So there are multiple ways to do it. One is to just throw more data and more prompts at it, but again, there's a limitation to that. Another is to fine tune LLMs. So once you have collected big enough data set, or I would say like the data set I have for the Stack Overflow also is pretty decent enough. You can fine tune your LLMs to be domain specific. Like I want the LLM to be a teacher, to just do those kinds of things. And Databricks has a nice course on this, on fine tuning LLMs. You essentially train the last two layers of these LLMs on whatever data you have provided. But the third one is the one I'm most excited about. It's the knowledge graphs. So currently, I may be using Neo4j, but I'm not using it to the most extent of what a graph database could be. So when what I mean with knowledge graph is, right, when you're extracting all this information, rather than directly generating embeddings and storing, you can summarize these information as facts, and then you try to store these facts in your graph database, and you somehow connect these facts to each other, and that builds up a knowledge representation of your business logic or your domain logic. And rather than using vector similarity searches, you can use traditional graph traversal algorithms for searching. Just run a shortest path algorithm to see what facts are closer to my current fact that I'm working on. And that way you can link up knowledge one another. So your summarization becomes very crucial here. Like, how are you extracting the actual knowledge? And these facts don't need to be that big. And this is something people are still researching on, like what's the best way to go about doing. You'll find a lot of blog posts of how people want to do stuff. Like one of the ways I tried doing was I tried like LLMs could generate like Neo4j queries for itself. So I'll give it the Neo4j schema, like this is how the data is, and I'll tell this is what I want. So it will try to come up with a query on its own, and that is the result I return it to the user. And it is kind of a mixed bag. Like sometimes it gives very good results, like it's even better than normal drag, but sometimes the query might be wrong, or it like doesn't understand the schema properly. But this is the way I did it is also still an extension of a RAG only, right? As part of RAG, I'm putting the whole database schema in it. So you can't go much further with that. But I know one of my friend working in ISI, he's doing like cutting edge research on how knowledge graphs can be more accurate and represented. But personally, I feel that is the future of RAG, and that is the reason I wanted to start with graph databases, because that's how these knowledges will finally be provided to LLMs. So all these links are available here in my PPT also. I'll just share it if you want. And that's it for this part. So if you have any questions, or if you want me to elaborate on any of the technologies, you should let me know. Otherwise, I'll just do a small talk on Neo4j and how that is useful. Questions? Okay. Thank you. I guess I have like 40 minutes. I'll just show you Neo4j. It's, I don't think like a lot of people do use Neo4j as a database, but Let me just show you how this data actually looks in my system. So this particular URL, so this is just the Neo4j dashboard, you would say, that you can connect to, and I have connected it to the Stack Overflow database that I created. So I have some queries saved here. So you can see there are around 50,000 different types of objects currently in the database. And they can either be answers, questions, sites, tags, and users. And these are the relations, 75,000 relations. So an answer relation is between a question and an answer, the provided site, and the tagged relations. Uh, there is one thing I should do. I have a few queries saved. So let's just run the view all query. So I can see the actual query is this. So the Neo4j query language is called Cypher, and it is very much inspired from SQL. And I feel it's much more ergonomic. So you have a lot of clauses. So like match node, return node. Okay, this will be a bit slower. I'll just say limit 300. So match node and return node, what match node is does, right? So it tries to match over nodes, but since I'm not providing any filtering, so it will match over all nodes, and then it will return all the nodes. And I want to limit it. By default, this thing, right? This GUI visualization, if you load more than like 500 nodes, it gets very slow. That's a browser limitation. But if you don't put the limit 300, it will still try to return all the nodes. And in this case, it would have been 50,000 nodes. So that's why I added a limit so the query executes faster. Uh, but this graph data can be pretty exciting to see like what's actually happening and how these things are connected together, right? So uh, like right now, it just selected 300 of the first nodes and loaded. So we just have only one orange type of object. That's the website. This is Stack Overflow, but usually sometimes you'll have like math.stack exchange, physics.stack exchange, and you see all the questions have a site relation to it. So your purple objects are your questions, and the relation on them is the site. And any of these objects that you do, right, on the right, you'll see the metadata. Currently, my relations don't have any metadata, so they're empty. But if you look at like a site, this is where you'll have your body, your embeddings, creation date, and you can just consider it as your columns in your SQL databases. That's what this represents. The benefits of a graph database, first of all, is you can have a lot more connections rather than because the amount of SQL joins or like foreign keys you increase in a SQL database will hit a limit soon. It impacts the performance a lot. But graph databases are optimized for data that have a lot of dependencies and connections between each other. And due to its graph structures, you can use all your graph traversal algorithms also on it and find out interesting characteristics about the data. I can do like a Dijkstra's algorithm on it, but one thing I'll tell you, this current schema or the data set I have is not in the most optimized way for a graph database. Like if you look at the relations and the entities, these are still very hierarchical because you have questions, you have users, you have answers, you have sites. This still feels very SQL-esque, right? And these relations also form like a tree. There is like no cycles or something that's happening here. It's all like flowing down from site to questions to answers to users. So it's still not the best. Like I'm not fully utilizing Neo4j to its maximum capacity because the graph structure isn't that interesting right now. That's why I would say the knowledge graph representation would be very interesting because if you have, just imagine this, you have like facts and all your nodes are interconnected among each other. That's an interesting graph structure. That's a dense graph. You could do a lot of interesting things with that. But this is what Neo4j is. I'll just run some more queries. So like if I want questions from a particular site, the way you do filtering in Neo4j is basically like a JSON filtering. So if I say that the object S is of type site, I give it like a JSON. Its name should be Stack Overflow. And then you use this arrow syntax to define the relation what I want. So I say that the relation R should be of type site. And if I want to do filtering on relations also, right, I could add another JSON there. And then I say the other thing I want is the Q. So this Q, R, and S are now variables, and the colon defines their type. And while returning them, I can tell, okay, which variables I want and which is the limit. So this way I'll get like the 100 questions from that site. And similarly, as I showed you that early vector retrieval query, it is that thing only. It's just it has a lot more filtering in it. So you say I match nodes on questions, then I rename those variables as something else because it helps me in the query. So I rename node as question and the score property similarity. Then I match those questions on sites. I give it a site name. And again, the next thing I do is a sub expression. This is like a sub query. So you do another query inside a query. It's an aggregation result in a way. The reason I do this is because for each question, I'll have multiple answers. So I want it to run for all the answers. So you just match questions with answers. You order by whether they were accepted and also a descending order of their scores. Finally, you collect the answers. So I want the answer. Instead of getting multiple answers, I want them in an array. So I use the collect function on answers, and the two defines the number of answers I want. And this array is stored as the answers variable. And finally, I reduce all the answers array into a one giant string because at the end, LLMs are just going to take a string, right? So you concatenate the answer as a string. You say whether it was accepted, you add the score. And this is just building up a markdown syntax here. And finally, this answer is that answer string is added to the bigger question string. So the result of this whole thing will be a giant string, like multiple strings, and they will be ordered by similarity. And this is your actual vector similarity here. So you just pick up the top two similarities or whatever your LLM parameters, the K parameter, if you remember, defines. So if you say 2, it will pick up the top two similarities, and that is what's passed to the LLM. So the queries can look a bit complicated, but you need to look at like I feel it's more intuitive than SQL because it takes some inspirations from JSON also and how JSON filtering of object works. So that's just Neo4j for you. Just try to use it to model any kind of data you want. Uh, but just keep it in mind to not use it in a SQList way. Otherwise, you're not, I mean, I'm technically trying, still using it as a SQList way, but you're not getting the full benefits out of it. You need to rethink your data modeling when you're using a graph database. It's not a SQL database. So again, you can go to the Neo4j docs. They have nice workshops and they are doing a lot of stuff for Gen AI. So hope that helps you. So yeah, that's it for me today. I'll leave my QR codes if you want to connect with me in the future. That's it. Thank you.